Welcome to Saltwater Stories. I'm so glad you're here because today we're setting out on an adventure unlike any other. Imagine for a moment the immense, mysterious world hidden beneath the ocean's surface. It's a place of incredible secrets, yeah, alien landscapes, and wonders that they defy belief. Most of this vast realm, covering over 70% of our planet, it remains way beyond our direct reach, cloaked in crushing pressure and, eternal darkness. But what if I told you we have found a way to reach these extreme depths, to uncover those secrets, and to bring the wonders of the abyss right into our homes? Today, we're embarking on a journey to explore the incredible machines that have become our eyes, our hands, and even our scientific brains in the deepest parts of the ocean. We're talking about AUVs, that's autonomous underwater vehicles, and ROVs, remotely operated vehicles in ocean exploration.
That's absolutely the mission for our conversation today. To really understand these astonishing robots, how do they actually work their magic in such an unforgiving environment? I mean, the pressure alone is incredible. And what amazing discoveries are they allowing us to make? And maybe most importantly, why are they no longer just, fascinating gadgets, but truly indispensable tools, essential for understanding our planet, especially as we grapple with huge challenges like climate change and, well, managing our ocean resources responsibly? These mechanical marvels are genuinely revolutionizing how we interact with the blue heart of our world.
Okay, right, let's get into this. It's fascinating stuff. When we talk about venturing into these unseen frontiers of our oceans, these robots, known collectively as unmanned underwater vehicles or UUVs, they're our most crucial partners. Think of them as highly specialized robots, engineered specifically to work underwater. They let us go places that are just too dangerous, too deep, or honestly just too expensive for human divers or even manned subs to explore safely or, effectively. They really extend our reach further than ever before.
Absolutely. And what's really key here is that within this big family of UUVs, there are two main categories we need to focus on: remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs. Grasping the fundamental differences between these two is, well, it's crucial to understanding why each one is so special and how they contribute in their own unique ways. It's like having different tools in a really advanced toolbox, each one perfect for a specific job down there.
Okay, so let's start with the ROV. Picture this: an unoccupied underwater robot, but one that's still very much connected to a ship on the surface. I often think of it like a high-tech puppet on a really, really long, super strong string. That string is what we call a tether or an umbilical, right? And that's its defining feature, its lifeline, basically. It's constant connection to us up top.
And that tether, it's way more than just a simple cable. It's an engineering marvel in itself. Imagine it like a super tough high-speed highway. It sends power down and data back up all at the same time. It continuously transmits electrical power from the ship down to the ROV, which is critical, right? Because it means the robot never runs out of juice during a long mission. And at the same time, it carries commands from the human operator on the ship straight to the robot's thrusters, its cameras, even its little manipulator arms. And crucially, in the other direction, it sends back all that high bandwidth info, multiple streams of HD video, sensor readings, all in real time to the control room on the ship. It's a constant, seamless two-way street.
That real-time human control, that's exactly what makes ROVs so incredibly versatile, isn't it? You can imagine a dedicated team on the ship using joysticks and complex controls, basically piloting the ROV as if they were right there in the deep, looking through its cameras. This direct-to-me control means ROVs are perfect for those delicate, really complex tasks that you just couldn't pre-program. We're talking about like carefully collecting fragile samples without breaking them, doing intricate science experiments right there on the sea floor, or fixing important underwater equipment, think subsea cables or those huge oil and gas structures, or even just getting stunning close-up video of amazing things like old shipwrecks or those super hot hydrothermal vents that spew minerals. And they come in all sizes too, right? From small observation class ones just for looking around to massive work class ROVs that do the heavy lifting in industries like offshore energy.
Yeah, exactly. Now, shifting gears a bit, let's talk AUVs. Well, they're quite a different beast altogether. They are the independent explorers. They are self-guided and completely untethered, no physical connection to the ship at all. You could maybe visualize them as the self-driving cars of the ocean, or maybe like a robot delivering a package all by itself. They get their instructions and then off they go, totally autonomous.
That's the key difference, yeah, the lack of a tether. Before an AUV even hits the water, scientists program it meticulously. They tell exactly where to go, what sensors to turn on, what path to follow. It's like giving it a super detailed map and a very specific to-do list for its entire journey. Then it launches, does its whole mission independently, and eventually comes back to a preset rendezvous point.
Hmm.
But unlike an ROV where you see everything live, an AUV stores all its data, sonar maps, photos, sensor readings on board. You only get to download and look at all that precious data after it's safely back on deck. So no live video feeds, no making adjustments on the fly based on what it sees.
Which brings up a key point. How do they power themselves without that tether? AUVs are self-powered, typically using rechargeable lithium-ion batteries, much like an electric cars, just, built for the ocean. This naturally means their mission duration is limited by how much energy they can carry on board. Now, early AUVs were pretty rigid, just following preset lines, like mowing a lawn underwater. But modern AUVs are much smarter. They have what we call adaptive autonomy. This means they can actually process sensor data during the mission and make intelligent decisions in real time. For instance, an AUV might be programmed to change its path if it detects an unexpected obstacle, like a big rock that wasn't on the map. Or it might even decide on its own to investigate something interesting it finds, like a chemical plume suggesting a nearby vent or maybe a sonar contact that looks like a shipwreck. It can adjust its plan.
Wow, okay. So when we put them side by side, the core difference really is that tether, or the lack of it. It's not just a wire. It totally changes how you explore, doesn't it?
Absolutely. Let's break down their features because it really clarifies why each one is so vital. Starting with the control method. RVs have that real-time human piloting. Operators see everything live, making instant decisions. AUVs, on the other hand, execute a pre-programmed mission. It's all managed by their onboard computers, no real-time human input during the run. Then, the tether. Present and essential for ROVs, providing power and that high-speed data link. Completely absent for AUVs, giving them that freedom but limiting real-time interaction.
Right. And the power source is another big one. ROVs get continuous power from the ship via the tether. So theoretically, they could run forever, or at least as long as the ship is out there. But AUVs carry their own power, usually those lithium-ion batteries we mentioned. So their time underwater is limited by how long those batteries last.
And that ties into data transmission. This is where the ROV's tether really shines. They get high bandwidth, real-time data and video back to the surface through fiber optics. You see what the robot sees instantly. AUVs, they have to store all the high-res data internally. It only gets downloaded after the mission. They might send back little status updates acoustically, using sound waves, but super low bandwidth. Think dial-up speed. Definitely no live video.
Okay, so thinking about what they're actually used for,
Yeah.
their typical missions. ROVs seem perfect for detailed inspections, like getting really close to something or carefully picking up fragile samples, doing complex tasks with their arms, maybe fixing equipment. They're like the surgeons of the deep.
That's a great way to put it.
Whereas AUVs, being untethered and efficient over large areas, they seem ideal for wide area seafloor mapping, big ocean surveys, or just monitoring large patches of ocean.
Precisely, which leads to their key advantage. For ROVs, it's that precise, real-time human control. Absolutely essential for tricky spots or tasks needing manipulation. For AUVs, it's the efficiency over large areas. They can map huge zones much faster and free up the ship to do other things simultaneously.
And the flip side, their key limitations.
Mm.
For ROVs, it's got to be the tether, right? Limited range based on its length and the risk of it getting snagged on stuff.
Exactly. And for AUVs, the main limits are battery life, how long they can stay out, and the fact that there's no way for a human to step in immediately if something unexpected happens or if they find something really cool that needs instant follow-up.
But technology doesn't stand still, does it?
Right.
We're seeing newer types like specialized or even hybrid vehicles that kind of blur these lines.
Oh, definitely. One really unique type is the underwater glider. These are a special kind of AUV because they don't use propellers or thrusters most of the time. Instead, they have this ingenious variable buoyancy engine. Think of it like a tiny internal balloon or bladder. They can pump a little water in or out, changing their overall density just slightly. This makes them a bit heavier or lighter than the surrounding seawater, so they slowly sink or rise. And as they do, wings, like on an airplane, but underwater, convert that vertical movement into forward gliding. They follow this sort of up and down sawtooth path through the water. And the amazing thing is it's incredibly energy efficient. Gliders can stay out for weeks, even months, traveling thousands of kilometers on very little power, collecting long-term ocean data.
Wow, months. That's incredible. And then you mentioned hybrid ROVs or HROVs, best of both worlds.
Kind of, yeah. These machines try to combine the strengths of both. They can operate autonomously, like an AUV, to cover a large area efficiently, maybe doing a broad map survey. But then if they find something interesting, say a potential vent site or an unusual sonar target, they can connect to a very thin, lightweight fiber optic tether. This connection then allows a human operator back on the ship to take over direct control, piloting it like a traditional ROV for close-up looks and maybe even grabbing a sample. So you get the scouting efficiency of an AUV and the precision of an ROV when you need it. Really clever.
Very cool. Are there other types too?
Yeah, there are other classifications, often driven by size and mission duration, particularly in defense. Things like large UUVs, LUUVs, and even extra large UUVs, XLUUVs. These are basically unmanned submarines designed for very long missions, pushing the limits of endurance and autonomy for potentially weeks or months at a time.
It's amazing how far this tech has come. But where did it all start? It's surprising, actually. The idea of AUVs kind of goes back to military needs, right? Like, the concept started way back in the mid-19th century with the self-propelled torpedo. Think about the Lupus Whitehead torpedo from 1866. It was propelled by compressed air, designed to follow a preset course underwater. In a way, that was one of the very first pre-programmed underwater vehicles. It had its instructions and just went.
That's a fascinating link. And for ROVs, while there were early attempts like Dmitry Rybakov's Poodle in 1953, the technology really got a major push from the U.S. Navy in the 1960s with their CURV program cable-controlled underwater recovery vehicle, designed specifically for deep-sea recovery jobs.
And CURV had that incredible success story in 1966, didn't it? CURVI, the ROV, actually located and recovered a lost hydrogen bomb from, nearly 900 meters deep off the coast of Spain?
That's right, 869 meters. An astonishing feat back then.
It really proved that robots could do complex, hands-on tasks in the deep sea, things humans just couldn't reach safely, a total game changer.
And it didn't take long for scientists to see the huge potential beyond just military or recovery tasks. As early as 1957, the University of Washington, with Navy funding, built SPURV, the Self-Propelled Underwater Research Vehicle. Significantly, this was the first AUV specifically designed for science. Its mission, to operate under the hazardous conditions of Arctic ice, collecting ocean data like sound transmission and water properties in a place way too dangerous for people back then.
And then the 70s and 80s saw a big leap forward, didn't they, with new tech?
Yeah.
Like acoustic transponders, those underwater GPS beacons you mentioned, helping them navigate accurately, and fiber optic cables for ROVs. That must have been revolutionary, getting crystal clear video back from the deep for the first time. Imagine seeing that.
Oh, absolutely. It changed everything for ROV operations. Suddenly, you could really see what was down there in detail. And during that time, we saw AUV projects popping up globally, too. SCAPT in the Soviet Union, EPILARD in France, P2OA in Japan, all pushing the boundaries of what these autonomous robots could do.
And then the offshore oil and gas industry got involved in a big way in the 80s.
Massively. The boom in offshore oil and gas exploration and production made UUVs commonplace. ROVs quickly became essential tools for things like inspecting pipelines, installing subsea equipment, helping with drilling. They were just so much safer and ultimately cheaper than relying on human divers for those demanding deepwater jobs. And later, AUVs came into play for doing large-scale seafloor surveys before construction or for inspecting those long pipelines after they were laid, often much more efficient than using ships.
And thinking back on specific missions, those landmark moments, that 1966 CURV recovery really stands out as proving the concept.
Definitely. And then the 1985 discovery of the RMS Titanic, that just captured the world's imagination. It was found using the towed imaging sled Argo, developed by Bob Ballard's team at WHOI. While Argo wasn't self-propelled, its success really showcased the power of remote vehicles for deep-sea discovery. And later, they used Jason Jr., an early ROV, to get those first iconic close-up looks inside the wreck. It really opened people's eyes to the hidden history lying in the deep.
And more recently, the 2010 Deepwater Horizon oil spill. That was a huge moment for UUVs, wasn't it? A massive mobilization.
Absolutely critical. AUVs like WHOI's Sentry were vital in mapping the extent of that enormous underwater oil plume. They used chemical sensors to essentially sniff out the hydrocarbons deep below the surface. But the most dramatic part was the work-class ROVs operated by the industry. They were the only tools that could operate at that depth 1,500 meters to get eyes on the damaged wellhead and perform the incredibly complex tasks needed to eventually cap the leak.
Wow.
It starkly demonstrated their critical importance, not just for science, but for environmental disaster response. They were literally the only things that could work down there.
Okay, so these robots are packed with tech. How do they actually sense the world around them down there?
Right, they're loaded with sensors. You can think of them as the robot senses, tailored for the ocean environment. Just like we use our eyes and ears, they use sound and light and other things.
Let's start with sound sonar, right? That's how they see far away underwater, because sound travels so well in water.
Exactly, and they use different types. Multi-beam echo sounders are amazing. They send out a wide fan of sound beams below the vehicle. By listening to the echoes returning from the seafloor, they can build up incredibly detailed 3D maps bathymetry, we call it.
Like drawing a 3D picture of the landscape below.
Precisely. Capturing canyons, volcanoes, fault lines in high resolution.
Okay, what else?
Then there's side-scan sonar. This gives you more of a grayscale image, like a detailed photograph of the seafloor texture to either side of the vehicle. It's really good for finding things lying on the seabed, like shipwrecks, or distinguishing different types of rock or sediment.
So less 3D, more like a wide black and white photo.
You got it. And then there's the sub-bottom profiler. This uses lower frequency sound that actually penetrates into the seafloor. It reveals the layers of sediment beneath the surface, maybe buried channels or structures like...
X-ray vision for the seabed.
Exactly. That's a perfect analogy.
Okay, sound is great for distance, but they need to see close-up too, right? Yeah. Cameras.
Absolutely. For close-up views, their optical systems are key. They typically have high-definition cameras, HD, often 4K these days as standard. But remember, the deep ocean is pitch black, so these cameras are always paired with powerful LED lights to illuminate the scene right in front of them.
Like super bright underwater flashlight.
Pretty much, allowing them to capture those stunning, clear images and videos of deep-sea creatures or geological features.
And they measure the water itself too, like its properties.
Oh yes, crucial stuff. Most scientific UUVs carry what's called a CTD package. CTD stands for conductivity, temperature, and depth. Conductivity tells you how salty the water is, temperature is obvious, and depth uses a pressure sensor. These measurements are fundamental for understanding ocean currents, water masses, how things mix, basically the ocean's physics. It's like a basic health check.
A smart thermometer and salt meter combined. Got it.
And they can carry lots of other sensors too, measuring dissolved oxygen, pH, acidity, chlorophyll that indicates tiny plant life, even water clarity or turbidity. It's like taking the ocean's pulse and running a whole battery of tests.
Are there other specialized sensors for finding specific things?
Definitely. Magnetometers are quite common, especially for archaeology or geology. These detect tiny variations in the Earth's magnetic field. Big metal objects, like a steel shipwreck, create a magnetic anomaly. Certain types of volcanic rocks do too.
So like a super sensitive metal detector for the deep ocean.
Exactly. Helps them find things hidden on or even just below the seafloor that sonar might miss.
Okay, so they can sense things. How do they actually move around? Propellers.
Mostly, yes. They use electric thrusters. Think of them as small underwater propellers driven by electric motors. To get full control forward, back, up, down, sideways, and rotating, they usually need at least 6 thrusters positioned carefully around the body. Some AUVs, especially the torpedo-shaped ones built for speed and distance, might just have one main propeller at the back for thrust and use fins, like an airplane's wings and tail, for steering and depth control.
And those gliders you mentioned earlier, they move differently.
Totally differently. Remember their buoyancy engine. By changing their buoyancy just slightly, they sink or rise, and their wings turn that vertical motion into forward gliding. It's the most energy-efficient way to travel underwater for long distances. Really clever design.
Right. And power, we touched on this, but let's recap. ROVs get power through the tether.
Correct. A continuous supply of high-voltage power from the ship. Their operating time is basically unlimited by power constraints.
While AUVs carry their own batteries.
Yep. Usually big packs of lithium-ion batteries. That's their main limitation on endurance right now. Though there's lots of exciting research into hydrogen fuel cells, these could potentially extend AUV missions from maybe a day or so to weeks. That would be a game changer for long-range exploration.
And that ROV tether, it's not just a power cord and data cable, is it? There's more to managing it.
Good point. Especially for deep operations or work near the bottom, managing the tether is crucial. They often use a tether management system or TMS. Think of it like a sophisticated underwater winch or maybe a garage that the ROV flies out of. The TMS sits between the main heavy umbilical cable coming from the ship and a shorter, more neutrally buoyant tether going to the ROV itself. It helps isolate the ROV from the ship's pitching and rolling motions, keeps the tether from getting tangled, and lets the ROV work steadily near the seafloor. Very important for precise tasks.
Okay, this is maybe the trickiest part, navigating. You said GPS doesn't work underwater. So how on earth do they know where they are, especially the AUVs on their own?
That is the fundamental challenge of underwater robotics. No GPS. Radio waves just get absorbed by water almost immediately, so they have to use other methods. The foundation is usually dead reckoning combined with an inertial navigation system, INS. The INS uses really sensitive gyroscopes and accelerometers to track every tiny movement, every acceleration, every turn the vehicle makes from its starting point.
Like walking blindfolded but counting every step and turn.
Exactly like that. It knows how it's moving, so it calculates where it should be. The problem is drift error. Tiny, tiny inaccuracies in the sensors add up over time, so the calculated position gradually drifts away from the true position.
So how do they fix that drift? They must need other inputs.
They do. They constantly aid the INS with data from other sensors to correct that drift. A key one is the Doppler velocity log, or DVL. This sends sound beams down to the seafloor. By measuring the frequency shift, the Doppler effect of the returning echoes, it can calculate the vehicle's speed and direction relative to the bottom very accurately.
Okay, so it knows how fast it's moving over the ground.
Precisely. And a high-precision pressure sensor tells it its exact depth. Combining INS, DVL, and depth gives a pretty good relative position.
But they need absolute position too, right? To know where they are on a map?
Yes. For that, they usually rely on acoustic positioning. Sound travels well underwater, remember? One common method is ultra-short baseline, or USBL. There's a transducer on the ship that pings the UUV. By measuring the time it takes for the sound to travel back and forth and the precise angle the reply comes from, the system calculates the UUV's position relative to the ship.
Like a friend on the boat pointing and saying, "You're over there, that far away."
Kind of, yeah. It works well, but accuracy decreases the farther away and deeper the UUV is. For really high precision, especially for detailed survey work, they use long baseline, or LBL. This involves placing several acoustic beacons transponders on the seafloor in a calibrated grid around the work area. The UUV then measures its distance to several of these known points simultaneously and calculates its position by triangulation.
Like using underwater landmarks.
Exactly. It's very accurate down to centimeters sometimes, but it takes time and effort to set up the beacon network beforehand.
Okay, so they navigate, collect data. How does that data get back? Especially for the AUVs without the cable.
For ROVs, it's easy. Fiber optics in the tether. Super high bandwidth, real-time video, loads of sensor data, almost no delay, like fiber internet to the abyss.
Right, but AUVs, they use sound?
Yep, acoustic modems. They send data using sound pulses through the water. But the physics of sound in water means the bandwidth is really low. Very slow.
Like old dial-up internet slow.
Pretty much. Good enough for sending short status messages like current position is XYZ, maybe some basic sensor readings, but absolutely not fast enough for real-time video or transferring those huge sonar map files. All the big data stays on board until recovery.
Is anything changing there? Better communication tech coming?
People are working on it. Optical communication using blue-green lasers or LEDs is being developed. It can achieve much higher data rates than acoustics, but only over short distances, maybe a few hundred meters, and it needs a clear line of sight. So it might be useful for things like an AUV docking with an underwater station to quickly offload data, but it's not a solution for long-range comms back to the surface yet.
And the software that runs all this, the AUV's brain.
That's the Autonomy software. It's a complex system, usually layered. You have the navigation module fusing all the sensor data to figure out where it is. You have low-level controllers actually managing the thrusters and fins to make the vehicle move as commanded. And then the high-level mission planner is like the boss executing the pre-programmed sequence of tasks. Go here, turn on sonar, map this grid, maintain this altitude, etc.
How does it follow the plan? Is it just step by step?
Mostly, yes. It often uses what's called event-based autonomy. The mission is broken down into a series of steps triggered by events, like reach waypoint A, event 1, then start mapping pattern B until you cover area C, event 2, then turn on sensor D, event 3, then go to recovery point E, event 4. And researchers often use frameworks like ROS, Robot Operating System, to build these complex behaviors. It provides standardized tools and libraries to make developing sophisticated robot software a bit easier.
Okay, so we know how they work. What amazing things can they actually discover down there? What are the big applications?
Oh, so many. One of the most fundamental is just mapping the unseen seafloor. Because AUVs fly much closer to the bottom than ships, their sonar, especially multi-beam, can create incredibly detailed, high-resolution 3D maps. We're talking meter-scale or even centimeter-scale resolution. This reveals the fine details of underwater landscapes, canyons, volcanoes, fault lines that we simply couldn't see before from the surface. It's like seeing our planet properly for the first time in many places.
And that mapping is crucial, right? not just for cool pictures, but for finding things and contributing to projects like Seabed 2030.
Absolutely. Those detailed AUV maps are essential for pinpointing interesting spots for ROVs to investigate later. And yes, AUV data is a cornerstone of the Seabed 2030 initiative, that huge global effort to map the entire ocean floor by 2030, a massive undertaking.
What about exploring really unique places like those hydrothermal vents? How do they work together there?
It's often a fantastic hunter-gatherer approach. First, an AUV goes in to hunt. It does a broad survey, using its chemical sensors to sniff the water for the telltale signs of vent plumes, and uses its sonar to map the area and hopefully spot the vent chimneys.
So the AUV finds the spot.
Exactly. Then, the ROV comes in to gather. It goes right up to the vent site found by the AUV. Its HD cameras capture those amazing images of the weird and wonderful life forms, tube worms, strange crabs, bacteria mats, and its manipulator arms carefully collect samples of the hot fluids, the mineral-rich rocks, and even the delicate organisms for scientists to study back on the ship. Perfect teamwork.
That makes sense. What about really extreme environments like the poles, under the ice?
UUVs are perfect for polar missions, especially getting beneath the sea ice and floating ice shelves, places humans simply can't go easily or safely.
It's too dangerous.
AUVs, like the UK's Autosub Long Range or WHOI's seabed vehicles, can be deployed through holes drilled in the ice or from the edge. They then swim underneath the ice, mapping its underside and measuring its thickness with upward-looking sonar. This data is absolutely vital for understanding how fast glaciers and ice sheets are melting due to warming oceans, which directly impacts global sea level rise.
Wow. Are there ROVs that go under ice too?
Yes, specialized polar ROVs, sometimes called PROVs, they often have very long, thin fiber optic tethers, allowing them to explore maybe 10 or 20 kilometers under the ice, sending back live video of that hidden world.
That's incredible. And they've totally changed underwater archaeology too, haven't they? Finding shipwrecks.
Completely revolutionized it. They allow researchers to find, survey, and document shipwrecks far deeper than any diver could ever dream of reaching.
How does that process usually work? AUV first.
Typically, yes. An AUV does a large area survey using side-scan sonar to look for shapes on the seafloor, and magnetometers to detect metal hulls. Once it finds a promising target, an ROV is sent down for the detailed work. Visual confirmation, first of all. Then, the ROV uses its high-res cameras to capture thousands of overlapping images. This imagery is then used to create incredibly detailed 3D models of the wreck site through a process called photogrammetry.
So they can preserve it digitally without disturbing it.
Exactly. It allows archaeologists to study the wreck in detail virtually. This approach has led to the discovery of everything from ancient Roman ships in the Med to massive WWII aircraft carriers in the Pacific.
What about geology? Reading the rocks underwater.
AUVs provide the crucial high-resolution maps needed to understand geological processes like seafloor spreading at mid-ocean ridges or tectonic activity. Then, ROVs can go to specific spots identified on those maps and collect targeted samples, rock cores drilled from outcrops, sediment samples pushed into tubes, getting the physical evidence.
And this helps find resources too. Minerals or checking sites for wind farms.
Yes, the same techniques are used. Mapping potential mineral deposits, like those polymetallic nodules, or manganese crusts on seamounts. And it's absolutely essential for assessing the seafloor before building any large offshore structures like wind turbines or laying subsea cables. You need to know what the ground conditions are like.
And checking the ocean's health. Water sampling.
AUVs are fantastic mobile sensor platforms for monitoring. A single AUV, or especially a fleet of those long-endurance gliders, can patrol large areas, continuously collecting data on water quality, temperature, salinity, oxygen, chlorophyll, pH.
Which is crucial for tracking things like harmful algal blooms or ocean acidification from climate change, or detecting pollution like oil spills.
Precisely. They provide that wide area context, and ROVs can then be used to collect very specific water samples from precise locations or depths if needed, maybe right near a suspected pollution source or a deep-sea vent.
It's amazing the range of things they do. Can we talk about some specific famous missions or the big organizations using these robots?
Definitely. We mentioned the RMS Titanic exploration, 1985. Argo's discovery was huge, paving the way for ROVs like Jason Jr. to explore it. And tragically, the 2023 Titan submersible incident really underscored the role of ROVs in deepwater response. The ROV Odysseus 6K was the one that found the debris field, a somber reminder of their capability in emergencies.
And the Deepwater Horizon Response 2010, again, Sentry AUV mapping the plume, and the work class ROVs being the only things that could actually work on capping the well at 1,500 meters. Plus, scientific ROVs like Jason assessing the environmental damage afterwards. A massive effort.
Then you have the big research institutions, NOAA, the U.S. National Oceanic and Atmospheric Administration. Their ship Okeanos Explorer has a dual-body ROV system, Deep Discoverer and Sirius. They go down to 6,000 meters. And the coolest thing is they live stream their explorations. Anyone can watch online as they discover amazing things in the abyss. It's fantastic public outreach. NOAA also uses AUVs extensively for seafloor mapping for charts.
In WHOI Woods Hole Oceanographic Institution, they're giants in this field, right? Operating the National Deep Submergence Facility.
Yes, the NDSF. They provide vehicles for the whole U.S. science community. Their fleet includes the famous human-occupied sub Alvin, the 6,500-meter ROV Jason, and the workhorse AUV Sentry. Plus, WHOI developed the Remis AUVs, which are used worldwide, and Orpheus, designed for the absolute deepest parts of the ocean, the Hayatl trenches. They're real pioneers.
What about MBRI, the Monterey Bay Aquarium Research Institute? They're known for tech development, too.
World leaders. Based in California, they have the ROV Dock Wickets and a whole suite of specialized AUVs like the long-range Tethys and the mapping Dorado. MBRI often uses that integrated approach. We talked about AUVs scouted area first, then the ROV goes in for the detailed work based on what the AUV found.
Yeah.
Very efficient.
And the Schmidt Ocean Institute, SOI, with the RV Falcor, too.
Yes, operating the fantastic ROV Sebastian, known for its incredible 4K cameras and modular science skid. SOI is also hugely committed to open science, making all data public and live streaming their dives, really advancing accessibility.
And Ocean X, they combine science with media.
Right, a really interesting model. Their ship, Ocean Explorer, is like a floating production studio and advanced research lab combined. They have crewed subs, the ROV Chimera, AUVs, the whole package, focused on both exploration and telling compelling stories about the ocean. And all these efforts feed into things like Seabed 2030, that global push to map the entire ocean floor, relying heavily on AUV data from partners worldwide.
But it's not just research groups, right? The private sector operates huge fleets.
By far the largest fleets, yes. Servicing offshore energy, telecoms, etc. Companies like Ocean Infinity have really pioneered large-scale AUV surveys. They deploy many AUVs at once from a single ship to map vast areas incredibly quickly. And they're developing their Armada fleet, uncrewed surface vessels, USVs, that will launch and recover robots autonomously. That's the future for reducing costs and environmental impact.
And Fugro, they're a big player, too.
Huge global leader in geodata, massive fleets of ROVs, and increasingly, those USVs paired with electric ROVs, EROVs, for inspection, repair, and maintenance IRM work, especially for offshore wind farms. Fugro has also invested heavily in remote operations centers, ROCs, on shore. They can pilot ROVs anywhere in the world from land, which improves safety and efficiency dramatically.
So with all these options, how do people choose? AUV or ROV? It comes down to trade-offs, right? Autonomy versus real-time control.
Exactly. That's the core trade-off. The AUV's advantage is its independence. It can work away for hours or days without constant human oversight. This frees up the ship for other tasks, what we call parallel operations, makes research cruises much more efficient, perfect for systematic mapping or surveys where you know exactly what you need to cover.
But the ROV's advantage is that human in the loop. Indispensable sometimes, isn't it? The pilot can react instantly, use the arms for complex jobs, make decisions based on live video. Perfect for exploring unpredictable places like a wreck or needing to collect a very specific sample. What about endurance? Power.
ROV wins on endurance generally. That tether means theoretically unlimited operating time, limited only by crew or weather, not the robot's battery. Good for long, focused tasks at one site.
Whereas the AUV is limited by its battery life. Hours or maybe a few days for most survey AUVs, though gliders go for months. But it needs to come back eventually or get recharged somehow.
Then there's mobility and access. AUV has the advantage here. No tether means greater range, more freedom to roam, no risk of snagging the cable. Better for rugged terrain and generally faster.
But the ROV's tether can be a limitation. Range is fixed by its length, and it can get caught. Although the tether does help hold it steady in currents, maybe. And it's a way to pull it back if things go wrong.
True, it offers stability and a recovery lifeline. Trade-offs again.
And data. Communication.
Big ROV advantage here, too. That fiber optic tether gives high bandwidth, real-time data. Multiple HD video streams, sonar data, all instantly available on the ship. Scientists see everything live.
But the AUV is communication-starved, operates offline, essentially. All the high-res data is stored on board until it comes back. Acoustic comms are just too slow for video or big data files. Creates that data latency, you don't know what it found until later. Okay, so what's next? Where is this technology heading? What are the big innovations on the horizon?
It's a really exciting time. AI and machine learning are huge. They're turning AUVs from simple programmed machines into truly intelligent explorers.
How so? Making them smarter at navigating.
Yes, autonomous navigation and obstacle avoidance is getting much better. AI helps AUVs build maps of their surroundings in real time using sonar and cameras, and then plan safe paths through complex areas, even places like underwater caves or thick kelp forests where things are constantly changing. They can react and replan much better.
And analyzing the data they collect, AI helps there too.
Massively. Automated data analysis and anomaly detection. UUVs collect enormous amounts of data, terabytes sometimes. AI, especially computer vision, can sift through video or sonar data automatically, identifying species, geological features, maybe even trash on the seabed. This speeds up discovery immensely, and it enables science on the fly. An AUV could use AI to spot something unusual and decide on its own to pause its main mission and go investigate more closely.
That's seriously cool. But the power issue still limits AUVs, right?
Yeah.
What's happening there? Extended endurance.
That's still the biggest hurdle for AUVs, but progress is being made. Fuel cells, especially hydrogen fuel cells, offer much higher energy density than batteries. They could push mission times from a day to potentially a week or more. That's a major goal.
And the idea of docking stations, like underwater charging points.
Exactly. Underwater docking stations where AUVs can autonomously go to recharge wirelessly using inductive charging, like on some phones, and offload their data via a fast optical link.
An underwater gas station and data cafe.
Pretty much. These could allow AUVs to stay deployed for months, maybe even years, enabling truly persistent ocean monitoring without constant ship support.
What about teamwork? Robots working together. Swarming.
Yes. Inspired by fish schools or insect swarms. The idea is using many smaller, cheaper AUVs working cooperatively.
What are the advantages of a swarm?
Several. They can cover huge areas much faster than one large robot. The system is more resilient. If one robot fails, the mission continues. And they can work together, sharing information to map dynamic things like an oil spill or track a moving target like a whale.
And making them cheaper. Miniaturization and low-cost platforms. It's not just for big labs anymore.
Definitely becoming more accessible. Historically, these were multi-million-dollar machines. Now, companies like Blue Robotics offer modular ROVs for just a few $1,000s. This opens the door for smaller universities, schools, even citizen scientists.
And people are turning those cheap ROVs into AUVs.
Yes, adding low-cost sensors and computers. Plus, there are new portable AUVs like MBRI's MLA that are small enough to launch from a small boat or even the shore. Makes fieldwork much easier and cheaper.
So these robots don't work in isolation. They're part of a bigger picture, right? Integrated ocean exploration.
Absolutely. They work best as part of a larger system, combining data from different platforms to get a complete view.
Like using satellites first for the big picture.
Exactly. Satellites give you sea surface temperature, ocean color, plankton blooms, currents, ice cover. Helps you decide where to send the UUVs for a closer look.
And those uncrewed surface vehicles, USVs, the robot boats, they can act as motherships.
Yes, they can deploy AUVs, act as communication relays back to shore via satellite, and recover them.
Right.
Reduces the need for big, expensive cruise ships. Very efficient.
What about fixed platforms, moorings and buoys?
They provide that crucial long-term data at one spot. An AUV can swim by, download the moorings data, and also collect spatial data around it, putting the moorings time series data into context. They can complement each other perfectly.
And humans still have a role. Manned submersibles, HOVs like Alvin.
Still vital. Often, an AUV will do the initial wide area search. Then, an HOV or a high-capability ROV goes down with human eyes, or direct control, for detailed observation, complex sampling, or experiments that still require human intuition and dexterity. The real power comes from data fusion. Combining the high-resolution UUV data with broad satellite views and long-term mooring data gives a much more complete and dynamic understanding of ocean processes.
You give an example.
Sure. Imagine a satellite sees an unusual plankton bloom. A glider goes through it, measuring water properties. An AUV maps the seafloor beneath it. Then an ROV dives to sample specific animals reacting to the bloom. It's a tiered, responsive system, maximizing what we learn.
Okay, but with all this activity, we need to think about being responsible, right?
Right.
Ethics and environmental impact.
Absolutely critical. As these robots become more common, we have to consider their footprint.
What are the main concerns? Impact on ocean life? Noise?
Noise pollution is one. Thrusters make noise. which could potentially disturb marine mammals like whales and dolphins that rely on sound. So researchers are working on quieter propulsion.
What about physically bumping into things? Or the lights?
Physical disturbance is a risk, especially near fragile habitats like coral reefs or deep-sea sponges. Need careful piloting and navigation. And light pollution from the powerful lights can affect deep-sea creatures adapted to darkness. Need to use lights judiciously.
And if one gets lost? Pollution and marine debris.
That's a big concern. A lost UUV is marine debris. Its batteries could eventually leak harmful substances. So, responsible design uses non-toxic materials where possible, and robust recovery systems are essential to minimize losses. And a huge emerging issue is deep-sea resources. UUVs are the main tools finding potential mineral deposits. As deep-sea mining becomes technically feasible,
It raises massive questions about protecting those unique, poorly understood ecosystems, doesn't it? We need rules and protected areas before mining starts on a large scale.
precisely. The potential impacts are enormous, and we know so little about many of these deep environments. Precaution is essential.
What about the data and rules? Who owns the data collected in international waters? How is it shared?
Complex questions with no easy answers yet. When AUVs cross maritime boundaries on long missions, we need clear international protocols, like we have for ships and planes, to ensure operations are safe, cooperative, and environmentally sound. Data sharing policies are also crucial for maximizing scientific benefit.
So looking at the big picture economics and challenges, this is a big market now.
Multi-billion-dollar market and growing fast, projected to maybe double or more in the next decade. ROVs are still the bigger slice of the pie currently, mostly due to offshore energy, but AUVs are the fastest growing segment.
And the main drivers are offshore energy, both oil, gas, and especially wind farms now, plus defense, research, environmental monitoring.
Exactly. Offshore wind is becoming huge. Installing and maintaining all those turbines and cables requires vast amounts of UV work. Defense is always big mine hunting, surveillance. And the need for better ocean understanding for climate science and resource management keeps growing.
And the main cost trend is saving money and improving safety by replacing divers and using those uncrewed surface vessels and remote operations centers.
Yes, reducing human risk in deep water is a primary benefit. And the move to remote and autonomous operations drastically cuts ship time, fuel costs, and emissions. Big economic and environmental wins, even though the initial robot investment is high.
But there are still challenges ahead. It's not all solved.
Far from it. Autonomy in really complex places under shifting ice, inside wrecks, dense kelp is still very hard. Robots struggle with the level of situational awareness needed.
Reliability and recovery, too. Losing a multi-million-dollar robot must be painful.
Extremely. The deep ocean is harsh. Component failures, connector issues, software glitches. Ensuring extreme reliability and having solid backup recovery plans is paramount, especially under ice.
And that data transmission bottleneck for AUVs, still a major issue.
Still the biggest hurdle for real-time AUV operations. Acoustic comms are just too slow for big data or video that deploy, wait, recover, download, cycle, slows down discovery.
Power and endurance for AUVs, still pushing for longer battery life or practical charging.
Always a key focus. Better batteries, fuel cells, and those underwater docking charging stations are all areas of intense development.
And lack of standardization. Different systems don't talk to each other easily.
Yeah, lots of different companies, proprietary systems makes it hard to swap parts or integrate data easily. More common standards would really help the whole field move faster.
Okay, so looking even further ahead, beyond Earth, beyond imagination, you mentioned exploring alien oceans.
Perhaps the most exciting long-term prospect. Scientists are increasingly convinced that moons like Jupiter's Europa and Saturn's Enceladus have huge liquid water oceans under their ice shells, prime places to look for life.
Wow. So we'd need super robots to get there.
Exactly. A new generation of hyper-autonomous robots. Things like WHOI's Orpheus AUV, designed for Earth's deepest trenches, are already testing technologies for a future cryobot that could melt through kilometers of ice and deploy a swimming robot into an alien sea.
Incredible. Just imagine.
And back here on Earth, we'll see next-gen robotics inspired by nature bionics. Robots that swim like fish, use jet propulsion like squid, or have soft, flexible bodies like octopuses for manipulation, mimicking nature's solutions for efficiency and maneuverability.
And those fully autonomous swarms becoming reality. thousands of tiny robots working together.
That's the vision. Dynamically mapping huge areas, tracking shifting ocean features or animal migrations in real time, acting like a distributed intelligence sensing network across the ocean. And those docking stations enabling resident vehicles, a permanent robotic presence on the seafloor.
Yeah, AUVs living underwater near wind farms or observatories, emerging to do tasks, recharge, and wait for instructions, staying down for months or years.
That's the goal, a truly persistent presence, collecting continuous data without constant ship support. Game-changing for monitoring.
And finally, a vital role in climate change monitoring.
Absolutely crucial. As climate impacts accelerate, fleets of long-endurance AUVs and gliders will be the backbone of our global ocean observing system.
Providing the high-resolution data we desperately need to improve climate models, forecast changes in temperature, acidity, sea level, maybe even help with tsunami warnings.
Potentially, yes. Their role in understanding and helping us adapt to our changing planet is only just beginning and will be incredibly important.
Wow, what an incredible journey we've taken today, exploring the amazing world of AUVs and ROVs. Thank you so much for joining us on Saltwater Stories.
Yeah, it's been great. And we really hope that you, listening, now see these robots not just as, cool machines, but as essential partners in our huge quest to understand this planet's biggest, least explored frontier. It's an amazing story of ingenuity and discovery, isn't it?
It really is. And just think, imagine what more we'll uncover in the next few decades with these robotic explorers leading the charge. New species, hidden geological wonders, vital data to help us protect our shared blue planet. The ocean still holds so many secrets, and these machines are really just getting started. See you next time for Saltwater Stories.